Hello everyone. This is section 2.5 where we discuss measures of position. So in the previous sections we looked at measures of central tendency, how to locate the center of the data, and then measures of dispersion, how the data is spread out, and now we look at how the data is in terms of the position of a piece of data. So when we have a data set, we can split it up into what are called fractiles, either percentiles or deciles. So the percentile is most commonly used, and percentage is 100 parts. Quartiles are a common thing to indicate the position of some data, and as it suggests, quartiles split the data into 4 equal parts. And so we have the first quartile where 25% of the data fall on or below. Whenever we talk about percentiles, the basic definition for percentiles means the amount of data below a particular piece of data. So that's important to remember. So first quartile, 25% is below. Second quartile is actually the median, 50% of the data is below. Third quartile, 75% of the data. And then we have what we define as the interquartile range. It's the difference between the first and third quadrants, or quartiles. So that's a formula to remember. And to display the set of data, we often will use what's called a box and whisker plot, or just a box plot. And it includes what we refer to as the 5-number summary, which contains the following: the minimum entry, the 3 quartiles, and then the maximum entry. And when we draw a box plot or a box or whisker plot, we use the 5-number summary, as mentioned, and you could read through the directions. But here's an example of what it would look like. Our minimum entry on the left, the box contains the 3 quartiles, and then our maximum entry on the right. So let's do so for this set of data. First off, you want to order it, because we have to find the 3 quartiles, and we'll do one order of smallest to largest, so 50, 51, 54, 67, 71, 75, 79, 83, 89, and 98. Okay, so first we find the median, noted as 10 pieces of data by inspection between the 5th and the 6th. So the median we said is actually Q2, Q sub 2, and because it falls between these 2 pieces of data, add the 2 pieces, divide by 2, and that gives us 73. Now, what we do to find the first and the third quartiles is you literally split that in half and find the median of each side. So the median to the left would be the third, or excuse me, to the right would be Q3, which is 83. That's the middle piece. And the median for the data set on the left is Q1, and that's 54, which is the median of those 5 pieces of data. So we could note also that the minimum entry is 50, and the maximum entry 98. And basically draw a number line. When I install the data, start at 50 is my low, so 60, 70, 80, 90, 100. You could use a straight edge and scale it, but rough sketch is fine as well. Okay, I like to start by creating the box first. So Q1 is 54. Somewhere about here I'm going to put the left end of my box. And then Q3 is 83. So right around here will be the right end of my box. And I'll just make that rectangle. And you could even note Q1 is 54, Q3 is 83 on the graph. The middle piece, 73, right about here. So Q2, 73. And then the whiskers, we'll stretch them out. Going to 98, right around here. Label that as my max. 98, and then to 50 is the minimum. And if you wanted to finish it off, if it were asked, the interquartile range, Q3 minus Q1, so 83 minus 54, or 29. Okay, so that's how we construct the box plot. And now for the last thing, this section, we'll look at standard scores. And this is something that once we start chapter 5, this is monumental. And once we start chapter 5, we'll be doing this on a daily basis. And we talk about the standard score or z-score. And it basically is just the number of standard deviations that the data value lies away from the mean. So how far is the data piece away from the mean? And there's a formula, it's given on our formula sheet. It's the data value minus the mean over the standard deviation, so x minus mu over sigma. So remember, mu is the population mean, and sigma, population standard deviation. Z-scores could be positive, negative, or 0. If it's negative, it's to the left of the mean or below the mean. If the z-score is positive, it's to the right of the mean or above the mean. And if the z-score is 0, it is the mean. So 0 is the mean. And because of the empirical rule, you might recall the 68, 95, 99.7 rule. Since 95% of the data lies between two standard deviations above and below the mean, when we calculate z-scores that are either greater than 2 or less than negative 2, we say that they're unusual. So we have a couple examples here. First off, the heights of adult males in the U.S. in this age group. Bell-shaped curve, so it tells us it's normally distributed. And gives us the mean and the standard deviation. So maybe off to the side I'll write mu is 69.6, sigma 3.0. further. Tells us there's 4 adults. Here's their different heights. We want to determine if any of these heights are unusual by calculating their z-scores. So again, the formula for the z-score, this is the way I make my z's. I always put a little line through it. So when I make a 2, it'll look like that, and when I make a z, it'll look like a 2, but I'll have a line through it. So just make sure you get used to that. And the z-score formula again is x minus mu over sigma. So that's the formula we're going to be going to. And we have 4 parts. So let me label them. Part A, for the data value x equals 69. Then we have that z is 69 is x minus 69.6 is mu over sigma 3.0, and that gives us negative 0.2. Good practice when you calculate a z-score, even though 0.2 is the negative 0.2 is the exact value, we usually will list a z-score to the nearest hundredth. So negative 0.20 might be a way to rate that. And we'll see why in chapter 5. But that's not unusual because it's not below negative 2 standard deviations or above 2 standard deviations. So part B, x equaling 80 inches. So now we have 80 minus 69.6 over 3.0. And that's approximately 3.47. So that would be considered unusual. And think about this practically. Although these may not be the true statistics, 69.6 inches is about 5'9", 5'9.6". And if you're 5'9", you're pretty close, so you're average. But if you're 80 inches tall, 80 inches is 6'8", and just thinking of a 6'8" person, that is quite unusual. Okay, continuing, x equaling 72. So 72 minus 69.6 over 3.0 comes out to be 0.8 exactly. I'll say 0.80. It's not unusual. And 63 inches. So 63 minus 69.6 over 3.0 equal to negative 2.20. That's more than 2 standard deviations below the mean, so that is considered unusual. So then a final example, basically just using z-scores in a different way. This person takes 2 different tests. A statistics test, so I'm going to set up the given values on the stats test. The mean was 63. And the standard deviation, so mu is 63, standard deviation, sigma is 7. And then they took a biology test. And on the biology test, the mean was 23. So it was 23, and the standard deviation is 4. Now they scored a 73 on the statistics test, so X is 73, and a 29 on their biology test, so X is 29. And we wanted to determine what score they did, what test they did better on. Now, if you told somebody you scored a 29 and a 73, you would probably assume that you did better on the statistics. But it's relative to what the mean and the standard deviation is. So what we do by calculating z-scores is standardize. So again, the z-score formula is x minus mu over sigma. And we standardize these two tests. So for statistics, we have 73 is x minus mu 63 over sigma, which is 7. That gives us about 1.43. Again, you want to round to 2 decimal places, nearest hundredth. For biology, x is 29 minus the mean, mu 23, over the standard deviation, sigma is 4, and we get 1.5, I call it 1.50, and now that tells us that we actually performed better on the biology, because we have a higher standard score. Alright, so that's the end of 2.5, which concludes the material for exam or unit test 1.